Alright, this is the screencast for blood vessels. First up, this is not necessarily in the objectives, but it's something that you should know just in general, right? And we go over this in lab as well. An artery is anything that carries blood away from the heart. So generally we think of the arteries as being red because they're carrying oxygenated blood away from the heart. And a vein is anything that carries blood toward the heart. And then in between the two, you have capillaries that connect veins. One other thing to point out while we're here, right? This sucker right there, that's called your hepatic portal vein. You might remember the hypophyseal portal vein or the pituitary portal vein. Just to remember that a portal vein is a vein that connects to capillary bed. So here you have a capillary bed that serves your digestive system, connected to another capillary bed in your livers by the portal vein. I said livers, I meant liver. You only have one of them. And then also, just as review, you want to remember when you're in the pulmonary circulation, things get a little switched up, right? Here is deoxygenated blood going away from the heart to the lungs. It's blue because it's deoxygenated, but it's going away from the heart, so it's an artery. And then your pulmonary veins, right, going to the heart, so they are veins, but they're carrying oxygenated blood, so they are red. And it's going to be the same way when we do the umbilical circulation, where the umbilical arteries are going to be purplish, and the umbilical vein is going to be red because the placenta is the oxygen source for a fetus. Moving right along, blood flow, you just want to understand what flow is. It's self-explanatory. Next slide. Pressure, you want to understand blood pressure. That we'll talk about actually a little bit more in lab, even though we don't have a good blood pressure activity for online classes. We'll still leave the blood pressure discussion to lab. More importantly, what we want to understand is resistance and the relationship between resistance, flow, and blood pressure. So as this says here, resistance is the opposition to flow. So if resistance goes up, flow goes down. And we want to keep resistance down because we generally want our flow to stay constant, at least to certain organs. And so if your resistance goes up, but you're trying to keep flow constant, that means your pressure goes up. And we want to keep our pressure in the right range, not too low, but also not too high. So first things to think about resistance is understand the three factors that affect resistance. The first two here on this page, as it says right there, remain relatively constant. The thickness of your blood does not change appreciably. It does increase in viscosity if you get dehydrated, but as I understand it, if you were dehydrated enough to significantly affect the viscosity of your blood, you would be in deep, deep trouble because your blood pressure would be way, way down, or your blood volume would be way, way down. Blood vessel length. This one also, once you're fully grown throughout your adult life, remains relatively constant. But there are differences between people, so especially if you are taller, this means your blood vessels are all longer, so you have a greater total systemic length, which increases the resistance and puts strain on the heart. And this is one of the reasons why tall people tend not to live as long as average or short people like me. Then you have blood vessel radius. This one we would talk about more if we had more time, but we don't. This does vary from moment to moment and from organ to organ. It is one of the mechanisms that your autonomic nervous system uses to direct blood flow. So if your sympathetic nervous system kicks in, blood vessels to skeletal muscle, peripheral blood vessels, are going to dilate. increasing flow, decreasing resistance. At the same time, blood vessels going to visceral organs like your digestive tract are going to constrict, decreasing flow by increasing the resistance, and this is going to direct blood flow to the skeletal muscle over the digestive system. And so your whole body controls blood vessels this way, and even blood vessels serving individual organs can vasodilate or vasoconstrict in response to the metabolism in that individual organ. Smooth muscle is really cool. It would be great if we had more time to talk about it, but we don't. Then looking at this graph right here, there is one important thing I want you to note. So what you're looking at is on the y-axis is blood pressure as measured in millimeters of mercury, and then on the x-axis is you're moving from the aorta through into smaller and smaller arteries, through capillaries, and then into the veins. I want you to note this steep drop in pressure as you move from the arterioles into the capillaries and then into venules. So by the time you are in veins, the pressure is very, very low. And there are two important consequences of this when we're thinking about whole body physiology. One is that your venous pressure is just very low, so you have to have mechanisms to ensure that blood gets returned to the heart. And the other is just to cast your mind back to the cardiac chapter when we were talking about the heart. And we said increased blood pressure or afterload decreases cardiac output. Increased venous return, which increases your preload, is going to increase cardiac output. And you might be tempted to think if your blood pressure goes up, it's pushing more blood everywhere. Venous pressure goes up too, and more blood comes back to the heart. But because of this drop off here, you can have a rise in blood pressure, which is measured in the arteries, and that is not going to translate into a rise in venous pressure. So if you're increasing your blood pressure, all it's doing is making it harder for your heart to pump blood, and it's not encouraging blood flow through the veins back to the heart. This we can go over real quick, but we'll also talk about it in lab. I would say just memorize those definitions there. The one thing you do want to know about blood pressure is that it is measured in your arteries, as I said, not veins. It's usually your brachial artery, so they're measuring the blood pressure at the end of your brachial artery in your elbow. And so systolic is when your ventricles are contracting, diastolic is when your ventricles are relaxing, or when your ventricles are in systole versus diastole. Here now we get to two possible open-ended questions for the exam: the respiratory pump and the muscular pump. The first one here is the respiratory pump, and you just want to be able to explain how it works. You can memorize this definition down here if you want to. I do think it's one of those things that's hard to put into just a few words. But the way it works is that normally, or when you are exhaled, your diaphragm is up, as it is here. When you inhale, your diaphragm comes down. So as your diaphragm pushes down, it's increasing the pressure in your abdominal cavity. So it's squishing all of your abdominal organs, putting pressure on your inferior vena cava, which runs through your abdomen, and then also creating a low pressure zone in your thoracic cavity because the volume of your thoracic cavity is increasing. So pressure goes up in the abdomen, down in the thorax, and that squeezes the blood up into the thorax. Then when you exhale, your diaphragm goes up. Now you're creating a low pressure zone in your abdomen, or at least decreasing the pressure in your abdomen, and this makes it easier for blood to flow up from your legs into your abdomen. Next up then, this is just and I should go back and just point out, right, if you're exercising, your muscles are working hard, so you're going to be breathing faster. If you're breathing faster, you're increasing the effect of your respiratory pump. So the simple mechanics of breathing increase cardiac output during a time when you need increased cardiac output. Now, both of these pumps are just sort of really neat examples of how your body just mechanically works very well. So the muscular pump, this happens because the veins, or your veins, have valves in them. So if we look at just this vein right here, this valve right there and that valve right there only let the blood move up. So if you are a vein, or the blood in a vein that is next to a muscle inside of a compartment, when the muscle contracts, that puts pressure on the veins and pressure on the blood. And because the blood can only move in one direction, when your muscles put pressure on your veins, it pumps the blood back toward the heart. So again, the act of using your muscles is going to increase cardiac output at a time when you need more cardiac output because you're using your muscles. It's just really cool. Those two things are two of my favorite things about the body, and that's blood vessels in under 12 minutes.